Hi everyone, so today we're going to be going over another inclined plane question. This one's a slightly more complicated because it does involve friction. So let's get started. So the question is, a Mars rover 80 kilograms spots some cool rocks at the bottom of a Mars mountain and rolls down to it at constant velocity. If the mu of friction is 0.6, what is the angle of the hill? If there's a gust of wind coming from the bottom that causes the rover to accelerate 3 meters per second up the incline, find the force of the wind. Okay, so let's get started with its setup. So the first thing we want to do, as usual, is to draw a diagram of what's happening. So if we have the inclined plane over there with theta, and this is a rover that's sliding down. All right, then the next thing to do is to draw a free body diagram to figure out all the forces acting on it. So that's the rover. We have Fg, of course, pointing down, and then Fn coming straight out of the incline. And then we have friction. So since it's sliding down, friction is going to oppose this motion. So the vector for friction is going to be going in the opposite direction. Like that. Okay, and let's go ahead and start drawing the vector addition diagram. So you have Fg pointing straight down and Fn like this, and F of friction is going to connect right to the tail of the Fg vector. And note that there is no Fnet, so we don't need to draw a Fnet vector. And last but not least, this angle over here corresponds to this angle over here. And I went over this in my last video, so if you don't know why, go ahead and check that out. All right, okay, so we're done with the complete setup for this, so let's go ahead and start answering the first question. So the question is, if the mu of friction is 0.6, what is the angle of the hill? So if we look at this triangle over here, note that once again, it is a right angle triangle. So we could use all of those trig properties that we know. So according to this angle, the friction force is opposite to it, and the Fn is adjacent, and Fg is, of course, hypotenuse. So we can use one of these trig ratios to solve for the angle. So let's go ahead and use the friction side and the Fg side. So in that case, that's going to be sine, because friction is opposite to it, and Fg is the hypotenuse. So we can write the equation as sine theta is equal to the force of friction all over Fg. So if we keep on resolving this, what we get is, remember, friction is just mu times Fn. And that's just over Fg. And Fn, we don't know what Fn is, but we can once again use one of these trig properties. So remember that Fn is adjacent to this angle. So we could write cos theta is equal to Fn over Fg. And solving for Fn, what we get is Fn is equal to, so remember we just have to move that over there. So we get Fg cos theta. Fit the screen. Okay. And then we can plug Fn back into here. So we get mu times Fg cos theta all over Fg. And note that we can cancel the Fg's out. So we're left with mu cos theta equals sine theta. And we can divide over the cos on both sides. Cos theta, and note that, yeah, of course these cancel out. So you're left with sine theta over cos theta is equal to mu. And remember that sine over cos is just equal to tan. So we get tan theta is equal to mu. So now we only have one variable, so we can solve for this. So we can just take the inverse. So you get theta is going to be equal to tan inverse of mu, and let's just go ahead and plug what mu is. So you get tan inverse of 0.6, and let me calculate that. So get approximately 30.9637. So you can just round that up to, let's just do 31 degrees. So that is your final answer. So theta is equal to 31 degrees. So let's start to work on the second question. So it says, if there's a gust of wind coming from the bottom that causes the rover to accelerate 3 meters per second up the incline, find the force of the wind. So the diagram will look pretty much the same. Let's just draw some wind. That looks like wind. And now let's draw the free body diagram. So once again, the forces are pretty much the same. So we have Fg pointing straight down, and then we have Fn pointing straight out. And then we have the force of the wind that's pushing straight this way, Fw. And note that it's accelerating up the incline, and force of friction always opposes the motion. So friction is going to be down the incline now, like this. All right, so now let's go ahead and draw our vector addition diagram. So if we draw Fg, just like before, pointing straight down, and you have Fn pointing this way, then remember friction is like this. And then we have the force of the wind, and remember it goes up the incline, so it's going to go past this point over here. And then we have the Fnet force over here that connects with the tail of the Fg vector and then the head of the F wind vector. And we solved the angle from the last question, so this is equal to 31 degrees over here. So the setup is slightly different. All right, so let's start solving for Fw. So if you look at Fw, what it's equal to is it's made up of this vector here, the friction vector, this middle section here, right, of the triangle, and the Fnet vector over here. So we can rewrite that as F of friction, which is this component, then this component over here, which is part of the triangle. So remember that this is still a right angle triangle, just this portion over here, right? So we can call this side, let's just call this portion over here A, which is the side of the triangle. So once again, we can write a trig ratio for that. So if we do that, you have, this is the opposite side for the angle, and this is the hypotenuse, right? So we could write sine theta is equal to A over Fg. And if we just move that over, what we get is that A is equal to Fg sine theta. So if that's what A is equal to, we're going to plug that in over here. So we get Fg sine theta plus the last component over here, which is Fnet. All right, so that's our definition for F of W. So let's go ahead and start solving this. So remember that F of friction is equal to mu times Fn and plus Fg. So Fg is just equal to mg sine theta. And Fnet is equal to m times A. And remember from before that Fn is just equal to Fg cos theta, and Fg is just mg. So this is equal to mg cos theta. So let's go ahead and just plug that back into here. So we get mu times mg cos theta plus mg sine theta plus ma. All right, so now that we have all the components, let's go through and see if we know all the variables. So we do know mu, mg, of course, we know that. Angle we know, and ma. Okay, so we're good to go. So all we need to do now is plug in the values. So what we get here is 0.6 times m, which is 80 kilograms, times 9.8 meters per second squared, times cos 31. It's going to get a bit messy. Plus, once again, 80 kilograms times 9.8 meters per second squared plus sine 31, and then plus MA, which is 80 kilograms again, times 3 meters per second squared. All right, so let's plug that into the calculator and see what we get. Okay, so altogether I get 1,047.0 right on the dot. All right, so that is the force of the wind, and that's in newtons, of course. All right, so that's how you do this question. So thank you so much for watching. If you have any questions, once again, leave them in the comments below. And if you'd like me to do any physics questions, let me know as well. Thank you.